So last week of material we're going to look at is chapter 5. Okay, it's on 3 sections, 5.4, which we're going to split into 2 days, and then 5.5 and 5.6. 5.6, even though it's a different section, it's actually kind of a review of everything we're going to do in 5.4 and 5.5. So not like a formal review day, but it'll feel like a lot of material we've already covered. Has anybody ever heard or studied anything about vectors before? If you've taken physics, you probably have, but anybody ever studied them before? All right, so let me just kind of explain what a vector is. So in math or physics or for anywhere that you are going to try to use a vector to represent something, it's used when you want to represent something that has a magnitude and a direction. Okay, so an example of something that would have those two things would be if you took an object and threw it. There's 2 things you have to describe about that object. 1, how fast is it going from you throwing it? And 2, what direction did you throw it in? It's different if you throw something at 20 miles an hour, in front of you versus throwing it 20 miles an hour to the side of you. That's a different direction. So that's what a vector can represent. Something that has a magnitude and a direction. That example that I gave you about throwing something, that would be called a velocity vector. Another example would be what's called a force vector. So think of a force as just like something pushing or pulling. Right? If I were to push on this desk, and I push down with a certain amount of force. Well, the 2 things that are happening is I'm pushing down with a certain strength. That's like the number part. And there's a certain way that I'm pushing. Am I pushing down? Am I pulling up? Am I pushing it forward? What's the direction that I'm pushing on? All right, so that's another example of something we could use a vector to represent. Right, and we're definitely going to talk about this first one. I'm not sure if we'll do the second one. We'll see. See what happens. So we're going to look at how to represent vectors first. Okay, one way we can represent them is visually. And I think visual is good, usually when you're doing a word problem. Because in a word problem, you need to kind of see what's happening in the problem. But visual can take time. Okay? It's not always the most efficient way to do something because you have to sketch it. You have to draw it out. It's nice if you make it nice and straight lines or if you use a ruler. But again, that is time consuming. But it's how we'll do it to start out. So if we want to represent a vector and we're going to use an array to do it, well, remember, a vector has 2 things. It has a magnitude and it has a direction. The length of the array is the magnitude. That's how you could represent, for example, if you threw an object faster and you want to represent it as a vector, you could draw the vector longer. That's how it would be represented. If you were pushing on something and you wanted to push on it harder and you wanted to represent that as a vector, you could draw the arrow longer. A longer arrow means it's a bigger number, whatever that number is. Bigger force pushing, faster speed. You make the arrow shorter. That represents a weaker vector. Weaker could mean it's going slower. It could mean you're not pushing on something as strong. So that's the first thing we have to represent, magnitude. And what did I say the other thing was that a vector has? Yeah? Direction. Well, that's easy with an arrow. You just change which way it points. So the way that the arrow points indicates the direction. Now, at least in 2D, that's easy, right? Because all we have to do is just point it, up, down, left, or right, or somewhere in between. 3D starts to get a little harder to sketch in, and we won't really be doing any sketching in 3D. But 2D, we'll do some sketching. So now again, one of the downsides to sketching it is if you had a really big vector, does that mean you need to draw a really big arrow? Technically, yes. right? It means you need to make it really big. And if you don't have a big enough piece of graph paper, that can be a problem. So what can we do? We can scale it. So we can change the graph paper to say maybe each box represents 10 units instead of 1 unit. So you can do things like that, just like when you're graphing lines. You can change the x and the y scale. So vectors are directional. That's why we use an arrow. It makes a difference if you're pushing on something, say, to the left, or you're pushing on it to the right. That's two different directions. So the way we can represent it is, for example, if you were throwing an object and it went from point P to point Q, we could represent it with that symbol. And that's what you'd use in geometry. That's the ray PQ. This symbol right here, that doesn't actually mean it's going to the right. An arrow to the right above 2 letters in geometry just means that the 2 letters below it represent a ray, an initial point and a starting point. So if you wanted to represent, say, something going from Q to P, you would do this. QP under the ray. All right, so the first letter you put is always a starting point, and the second letter you put is the stopping point, or the direction that you're going. So again, I called P the starting point. You can call it the initial point. And Q, I called it the stopping point, but we also call it the terminal point. So let me show you, if I have an example. What I'm going to do is just going to bring up a grid, and I'm just going to mark 2 points, and then show you what the vector would look like. Okay, I'm going to go right back to that. I think I have a grid. There's my grid. So let's say that was point P, and that is point Q. Okay, so maybe a word problem we did, it gave us this information, and that's where we had to put the points. This would be the vector PQ. That's it. And if we wanted to find out the length of that, well, we can do things that we've done in the past, like make it into a triangle. We know this side is 4, and this side is 2. And what theorem do you think you could use to find the length of that vector? Yeah?
Slope.
So the slope would tell you like the steepness, but it wouldn't tell you how long it is. Yeah? Yeah, we could use the Pythagorean theorem. So a lot of things that we're going to do with vectors is going to involve making a triangle, and then either figuring out how long it is, which would be what we call the magnitude, or if we wanted, we could actually find that angle right there using trig, and that would give us the direction of the vector as an angle. So you'll see some of the stuff that we do is using things we've done before. Okay. All right, so that notation is fine. You can use it. That's from geometry. Another way you can write a vector, which you're going to see more in our book, is just a single letter. Well, the only problem with using a single letter is we already use single letters in math. When you write a letter in math, what does it usually represent? Or what do we call a letter in math? Oh, right?
Variable.
A variable. Well, a vector is not a variable. They're different things. So if we want to use a single letter by itself to represent a vector, we can do 2 things. One, we can make the letter bold. So anytime we see a bold letter in this section, that's how we know it's not a variable and it's a vector. Or you can use a single letter and put an arrow on top of it. Okay, the bold is generally the way that I'm going to do it. But it's just a little bit shorter way than having to write 2 letters to represent a vector. Just 1 letter. The book does a good job of showing it as bold because it's easy to do bold when you're writing out a font on a computer. When I do it on the board by hand, I'll just have to, if I want to make something bold, make it look like that. So anything you see that's bold is going to represent a vector. All right, so we're going to look today at 2 basic operations that we can do with vectors, which is adding them together. Now, I want you to think of vectors for a second as a force. So let's say I had a box right there. Let's say that there was a force pushing right, and then there was another force pushing up. What would happen to the box? Yeah. Yeah, it would move diagonally upward. It would almost be like if one force was just pushing at it at a diagonal, right? So when we have, let's just take these 2. I just want them as separate arrows. So that represents the force that's pushing to the right. This represents the force that's pushing up. And the result of that would be what I'm going to draw in green. Right there. So when we add 2 vectors together, you can just put that down. Thank you. When we add 2 vectors together, what ends up happening? You get a new vector. So in this example, when you combine the black and the red, you get the green. And I'm going to explain exactly how I did that, and that's what you're going to do. When you combine the 2 vectors together, they can point in a new direction, which in this case they do. The red one was up, the black one was right. When you combine an up and a right, you get the green one, which is now at a diagonal. Also, notice the length. The length changed. You can look at the length of the black one, look at the length of the red one, and the length of the green one is actually longer than either one of the 2 you started with. And that can happen when vectors are working with each other. Like if you push on something, and somebody else comes along and pushes, and you're each pushing in the same direction, well now you're combining your forces together and pushing. Compared to, let's say, you're pulling against each other. Well, like in a tug of war, if the rope isn't moving at all, it's not because there's not any tension in the rope. There could be a lot of tension in the cable. But if there's 50 people pulling it one way and 50 people pulling it the other way, what's happening is those forces are canceling out. So the result there could be 0. There could be no movement of the rope at all. But it's not because there's no tension in the cable. Just everything is balanced out. So that's kind of an important idea. We add 2 vectors together, you get a new vector. So the way I'm going to show you guys how to add vectors first is visually. Basically involves just drawing in a diagonal. But if you have 2 vectors, let me kind of explain. Let me explain it again as a picture, and then I'll write it out in words. So let's say that was vector v, and this was vector w. And you wanted to know what would happen if you combine those 2 together. So the first step is to line them up just like that. You line it up so that the end of one and the beginning of the other are the same point. And then the last step is to connect the beginning of the first one all the way to the end of the second one. So that would be the effect if you combine the red and the black. So the black is pointing right. The red is pointing right, but it also has a little bit of an up. So when you combine the red and the black together, you get an even longer vector pointing right, but it's also pointing a little bit up, and that's because of the red one. Right, so let me write out what I just did. All right, so V, W, those are bold. Just sometimes I don't make them bold. So position the vectors so that the ending point of V, that's the tip of the arrow, lines up with the starting point of W. And that's what I've done in that picture. Then to get the final answer, to get a picture of what the new vector would look like, you're going to connect the initial point of V all the way to the terminal point of W. And the example I showed you guys, it was just an example with 2 vectors, but you could do it for 20. You just have to connect them all. So I'll show you an example in a second, maybe with 3 or 4 vectors. Yep. So let me do 3. Okay, 3 different vectors. Say that's 1. That's 2. And actually, let's do a little different. Let's do 1. I don't have one way now. So I want to know what would happen if I combine all 3 of those. Well, this is what would happen. 1. 2, and 3. So you have to connect them all so that the end of one and the beginning of the next one all line up. And then you look at where did you start, where did you stop, and you connect where you started to where you stopped. We started here, and we ended there. So if you take these 3 vectors and combine them all together, you end up with that vector in green. It's a lot shorter than any of the original 2, and that's because a lot of these vectors are fighting each other. This black one is trying to point to the right and up, but this blue one is trying to point to the left and up. So it's fighting the black one a little bit. Both the black and the blue have an up part to them, but the red one has a really big down part. So it's like if these were all forces, they're fighting each other. They're not working together in this case. And you can see the way I connected them. I did this one, I did that one, and then I did that one. It wouldn't have mattered what order I did it. Let's say we did the red, then the black, then the blue. Now connect again where you started to where you stopped. And compare that to the one that we just had. It's the same. It doesn't matter what order you connect them in. If you do it properly, the result always comes out the same. So that kind of proves a point about addition. Does anybody remember the name of that? If you can add things up in a different order and it comes out the same? Like 5 plus 3, 3 plus 5. Remember what that's called? Begins with a C. That's commutative. Okay, so if you can add things up in a different order and it doesn't change the end result, that's what we call commutative. And vector addition is commutative. I'm going to write that down. I wasn't planning on showing that yet, but it just kind of came up. All right, so now let's try adding these 2 vectors up. So if you look at those two vectors, v and w, Ben, does it look like those vectors are fighting each other or kind of working together?
Working together?
Yeah, they're basically working together. One of them is pointing down and to the right. One of them is just pointing to the right. To be fighting each other, one of them would have to be pointing up and the other one pointing down a little, or one of them pointing right and the other one pointing left. Not happening here. Okay, so how do we add them up? It says specifically to do v plus w. So start with v. Not that the order matters, we just saw that. But start with v. Put w on the end. And then connect where you started to where you finished. So the answer is a picture. And there is an arrow there, you probably can't see it as well. And that's how you would add v plus w. We are going to do some things with vectors later on that are more numerical. And I'm going to show you an example right now of something you could do with vectors that's numerical. But for now, our answers are going to be images. Yeah?
So does it matter what side the arrow is pointing?
Can you say it again?
Like, you put the arrow specifically on that side, is that like...
Yes, direction is important.
Okay.
Because if we think of
If
these
you're
two...
both pointing that way, then the arrow goes that way.
So the arrow always goes from wherever you started to wherever you finished.
Oh, okay.
So if you imagine, like I can probably show it even better with more arrows. If you look at the path of arrows after you connect them all, it goes in a certain direction. The direction that it goes in stops somewhere. So this is the end, and then this is the start. You always connect the start of the path to the end of the path. And that's the direction of the arrow,
Okay.
from start to end.
Thank you.
Yep. Any other question on that? All right. So something you might see that would involve more numbers, if you think about all these different planes, it's a live view of the different planes that are in flight right now, they all have magnitudes and directions. The magnitude is how fast the plane is going. The direction is, well, the direction that it's flying. So if I click on any one of these planes, hopefully, it's more helpful to a computer if I can see the magnitude and direction as a number rather than as an arrow. So if we scroll down, we can see the magnitude is 266 miles per hour, so it looks like it's slowing down to probably come in for a landing. So 266 miles per hour, and if I click on the route, that is the direction. Okay, so these all mean something to a computer, but I can see what direction was it traveling, so it gives me a compass heading, and then it tells me how far that it flew on that part of the journey. So the thing that's more complicated about the airplane is the direction is always changing. So maybe it's going, one way a little bit, and then it turns a little, and then it turns again. So each one of these represents a turn that the plane made. Okay? And if you were to fly 360 degrees, that is north. So this plane was coming from Miami, and it said it was going to Boston. So you can see most of the directions that it traveled were close to the 360 degree range. Okay, it has to go a little bit east too to get from Miami to Boston. Most of them are pretty much north until it starts to get towards the end. Then it's making some small adjustments. But most of the big parts of the trip, like 300, 300, 200, 200 miles, they were all flying in the north type direction. All right, so every one of these planes you could think of as having a vector, and it's the job of the tower at each airport to control them all. A little more complicated than 2D because you also have 3D. So it might look like two planes are pretty close, but this plane could be at 9,000 feet and this plane could be at 30,000 feet. So it could be a big difference in between the two. All right, and there's all kinds of safety. They have to make sure that the planes are at least a certain distance apart, maintaining safe spacing when they're taking off. So there's a lot of different things to control, but vectors is one way that a computer could help someone to do it. We'll never be looking at a problem with this many vectors in it. That's a lot. Okay, but we'll probably do like up to two or three. All right, so let's look at these two. Before we add these up visually, anybody have a guess here? What's going to happen? Done?
You have no vector.
Yeah, so remember what you're supposed to do. Let's make different colors. So that's the start point. That's a start point. That's a terminal point, and that's a terminal point. To add these vectors up, you're supposed to connect the end of one to the beginning of the other. So we should be connecting that red one to that blue one. And then once we do that, you draw an arrow between this and that. But if you line these two up like you're supposed to, watch what happens to the other two. Okay. Lining up these two dots also lined up these two dots. So now when I connect this red one to the blue one, they're the same point. So I don't really have a vector here. Okay, what that's called, well, you can do it two ways. You can write it as a bold 0. You can't write it as the number 0, because remember what we said, if you add two vectors together, the answer is a vector. So you have to write a vector as an answer. Bold 0 represents the 0 vector. Or you could do it like that. Either one of these two answers is correct. The 0 vector, that's the only vector that technically doesn't have a magnitude or a direction, because its initial point and its terminal point are the same. So there's no length to it. And if you have 2 points that are the same, you don't have a direction either. Okay, so the 0 vector, that's kind of a special case. But this would be, if you think of a situation like a tug of war, that's exactly what's happening in a tug of war when there's no movement of the rope at all. The force pulling one way and the force pulling the other way are perfectly balanced, so there's no movement. But it's not because there's no tension in the rope. There's a lot of tension. Like if you were to cut the rope in the middle all of a sudden, everybody would fall on each side because there's a lot of tension. It's just perfectly balanced. Okay. Any question on that? So one of these we already saw, so I'm not going to spend too much time on it, but I will show you the other one. So vector addition is commutative. That means you can change the order you add vectors in, and you will get the same answer. Doesn't matter how many vectors you have. If you have 50 vectors, you can add them in any order, and you'll get exactly the same answer as if you added them in any other order. Just like adding numbers together. If you have 50 numbers and you have to add them all up, doesn't matter how you add them up, you're going to get the same answer. All right, so again, I'm not going to spend too much time, so I'm just going to do it really quick. So that's the left way, that's V plus W. Now if I do W and put V on the end of that, Again, I didn't use graph paper or a ruler, so it might not be perfect, but I hope it's close. Yeah, it's pretty close. It comes out the same either way. Okay, so that's the commutative property. Associative is a little different. That doesn't have anything to do with the order. A, B, C, A, B, C. That's exactly the same order on each side. Associative has to do with what you add first. Associative puts in a grouping symbol. This one I'll take a second to show. So here's 3 vectors. In your notes, I'm not sure how you really show this part because it's more of a visual of me moving things. So it might be better to just watch it. Here's A plus B. Now, if I was using graph paper, this would come out even better. But I'm going to try just to do it by hand. Okay, so there's A plus B. That's the green. Now, on the left side, it says to take A plus B and then add C onto the end of it. So I'm going to add C on the end of it. The green one's almost straight, but it does come down just a little. And now connect where I started to where I stopped. And that's the answer, doing it the way on the left. Don't need that anymore. Now, let's do it the way that it says on the right. Let's take B plus C and then do that part first. So here's B plus C. So if I do that, that's what you get in red for B plus C. Actually, I'm done with these now. And now let's add that onto the end of A. So here's A. Here's B plus C. And connect where you start to where you stop. And let's see how close that matches up with what we did before. Not bad. For not using a ruler or graph paper. It's pretty good. Okay, but vectors obey what we call the associative property. And you can change the order, or you can change what you do first. Okay. Any questions on that? Okay. So, this is an example of what we did. What number was it? Number 2. This was number 2. If you add 2 vectors that are opposites, like you take a vector and you add its opposite, you get the 0 vector. And example 2 showed you exactly what this means. Like if you have this versus that, the difference is this versus that. What's the difference between these 2 vectors? Yeah.
Direction.
Just the direction. There is no difference other than that. So when you put a negative in front of a vector, what the negative does is it spins it around 180 degrees. Doesn't change how long it is. It just makes it point the other way. So the difference between these 2, again, is the direction they point. They have exactly the same length. So any question about what putting a negative in front of a vector does? Now, I want you to look at that a little closer. Okay, and instead of using vectors, let me do actual numbers. But let me do a number plus a negative of a number. It doesn't have to be the same number. I just want to do something. Let's say we had, 4 plus negative 2. What's another way to think of that? 4 plus negative 2. Yeah.
4 minus 2.
Right, that's really subtraction. So what this is going to allow us to do is subtract 2 vectors. We already know how to add 2 vectors. Well, to subtract them, we're going to pretty much do the same thing. We're going to add the opposite of a vector. That's how you do subtraction. So to subtract 2 vectors, find the opposite of the second one and then add it. Why add it? Because we already know how to add it. We have a method for doing that. That's what I just taught you. But if you take the second vector and flip it around and then add it, you're really doing subtraction. Right? So I want to find v minus w. Can somebody tell me how would you think of v minus w as addition? Come?
V plus negative W.
Yeah. So what I'm really going to have you do is this. Find the opposite of w by flipping it around, and then add it to v. That's how you're going to do v minus w. All right, so first thing we need to find is we've got v. They'll give you that. They'll give you w. We need to flip w around. Well, if you have it drawn, the easiest way to flip it is just trace right over it and just draw it the opposite way. So there's negative w. Now, take v and add negative w. And what you're really doing is v minus w. So there's v. There's negative w. And final answer. That is v minus w. Right there. Any question on how we did the subtraction? So always think of subtraction as adding the opposite of the second one. That's how you do it. Visually. We haven't really done too much with numbers yet, but that'll be more tomorrow. All right, so we looked at adding, we looked at subtracting. Now we're going to look at what's called scaling a vector. Does anyone have an idea what that might mean? Like if I asked you to scale a vector, or think about like a scale model of something, what does it mean when you scale something? Yeah, Jake?
Making it bigger or smaller.
Exactly, that's what a scale is. A scale model could be a bigger model, like if you were making a model of a cell in science, you'd probably make it bigger so you could see it. Versus if you were making a scale model of a house, that would most likely mean it's a smaller version. But anyway, scaling something means to make it longer or shorter in this case. Bigger or smaller. So this is when you multiply a number, which we call the scale factor, okay, or the scalar, by a vector. Here's an example. That's a scalar product. It means to take vector v and triple it, or stack 3 of them together. That would be 3v. So when you scale a vector, you get a new vector. If you scale it by a number that's bigger than 1, you get a longer vector. If you scale it by a number that's between 0 and 1, like say 0.5, you get a shorter vector. But what do you think would happen if I did that? Two things would happen. Yeah?
It would get bigger, but it would also flip.
Yeah, so what would happen is it would get 3 times as long, and it would flip around 180 degrees and point the other way. This is the only way you can change the direction with a scalar, if you use a negative. So a scalar can do 3 things. It can shorten the vector if you multiply it by a number between 0 and 1. It can lengthen the vector if you multiply it by a number bigger than 1. Or it can reverse the direction if you multiply by a negative. So out of it, I'm going to have you guys find 2 vectors in a minute. I'll give you a picture of V. But which one there is going to make the vector longer? The 2V or the 1/2 V? Jade? 2V. How much longer is it going to make it?
Twice.
Yep, twice as long. So the way you would find 2V, if you had to do it, think of it like this. Take V, and then take another copy of it and stack the 2 together. There you go. That's 2V. Stacking 2 of them together. So this is where drawing can get a little annoying. Like if you had to maybe find 30V. Now you got to stack 30 of them together. So we probably want a more efficient way to do that than trying to draw out something 30 times as big. But I'm not going to have you do something that big. All right, and now how about 1/2 V? What's gonna happen there? Yeah.
Maybe shorten it by half.
Yeah. So it's going to become half as long. I don't have a way to do that exact on the computer. I mean, if I could multiply by 50% or something like that, I could. So I'm just going to estimate what's halfway. Maybe like that. Again, graph paper would solve this problem, but that's fine. Okay, so there's 2V and 1/2 V. Questions on those? All right. So let's find negative V and negative 1/3 V. Colby, what's going to be the difference between V and negative 1V?
Negative 1V would do the opposite of V.
Yeah, and when it's the opposite, how's that going to look? When you say it's the opposite, what will somebody see that tells them it's the opposite?
The arrow would be on the opposite side.
Yeah, it's going to point the other way. It's going to have no effect on the length at all. And that is something, if I want, I can do that exact on here by making a copy. And if you do a horizontal flip and then do a vertical flip, that's effective to rotating it 180 from geometry. Okay, so there's negative V. Now, negative 1/3 V is going to take what I just did and make it 1/3 the length. Again, I don't have a way to do that exact, so I'm just going to estimate 1/3, and we'll go with that. Okay, any question on that one? All right. All right, let's do this one, 2V plus 3W. So now it's combining the 2 things we did. We talked about addition earlier. We just talked about scaling. And now we're going to do both. So the first thing I need to find is 2v. All right, how would I find 2v? Yeah.
Double V.
Yeah, just take two of the v's and stack them together. So I'm going to do the whole problem right here. Let's just take that and make a copy of it. Where is the copy? There we go. All right, so there's 2b. And now what do I have to add on to the end of that? Go, Angelina? 3w. So now this is where you have to think ahead a little bit. Everything here is going to the right. So I probably should have started this problem way on the left edge of the page. I think I have enough room to fit 3w's. But if I didn't, I probably should have started further to the left. Okay, so there's 1, 2, and 3. And plenty of space. And now connect where you started to where the path of the arrow stops. And that is 2v plus 3w. Try to make the arrow big enough so you can see it clearly. But that's how you. Any questions on that? All right. So we've been talking about how vectors have two things, a magnitude and a direction. I even showed you how you find the magnitude. We didn't really do a problem formally, but some of you noticed it was Pythagorean theorem, because it's a hypotenuse in a triangle. And we're going to look more at that tomorrow. But this is the symbol that means magnitude. It's when you put double bars around a vector. So the thing inside here has to be a vector, and you put double bars around it. And that symbol means magnitude. Now the magnitude is always how long the vector is, so it doesn't matter which way it points. If you measure the length of an arrow, what kind of number are you always going to get? Yeah. Always going to be positive, unless it's the zero vector, in which case there wouldn't be anything to measure anyway. But magnitude is always positive. So now, thinking about that idea, okay, that magnitude is always positive, what would be the difference between those two things? The magnitude of the vector x and the magnitude of the vector negative x. Yeah?
The direction.
Okay, so I agree that the direction of them is different, but how about once you take into account what it's asking for, which is the length of vector x and the length of vector negative x. Yeah? They're equal. They're exactly the same. There's no difference between them other than the direction, which as far as magnitude goes, that doesn't matter. Okay, so those two things are exactly the same. All right, if the length comes out to exactly 1, there's a special word for that. Does anybody remember when we studied circles? If you had a radius of 1, that was called a certain type of circle. Anybody remember the name of the circle when the radius was 1? Yeah? Yeah, it's called a unit circle. Well, if you have a vector that comes out to exactly a length of 1, we call it a unit vector. So all that's special about a unit vector is that it's 1 unit in length. That's all. So this first section, there's a lot of vocabulary to kind of get through, but I'd say today will be the most, and then there won't be as much vocabulary tomorrow and Wednesday. All right, so last slide. So drawing vectors is great. I think if you have a word problem, it makes it very easy to see what's happening in the problem. But if you want to do something with vectors that's not a word problem, maybe drawing isn't the best way to do it. Drawing is time consuming. So you need a graph paper, so you need some kind of grid. You really need a straight edge. And you need to think about where you place things in the grid, because you can easily go off the page. So when we start doing more algebraic operations with vectors, we need a way to represent it other than doing a sketch. There are two ways you can represent vectors that are not sketches. I'm going to show you one today, then I'll show you another one tomorrow. These notations are purely numbers. They don't rely on a length of an arrow and which way it points. We don't need to do that. Kind of like when we looked at the airplane and we looked at the direction that it was traveling. They didn't draw an arrow on the screen to show us which way it was traveling. They gave us a compass heading. Well, we're not going to use a compass heading, but it's an idea that gives us direction, kind of like that. In our first notation we're going to look at that represents a vector without drawing an arrow. Our book calls it an algebraic vector. Okay, a couple important things about it. First of all, it's written inside angle brackets. That's what distinguishes it from being a coordinate. If you put parentheses, it's a coordinate. If you put angle brackets, it's a vector. Inside the angle brackets, there are two numbers because we're working in 2D. Let me go back to my grid for a second, and then I'll come right back to that. That vector has what we call two components to it. Basically, it's the direction. If you start here, and you stop here, how many units did you have to travel, let's say, to the right, to get from the start to the stop? Yep. 4. So you traveled horizontally a distance of 4, and vertically a distance of 1. So we would call that the vector 4, 1. This describes the horizontal movement. This describes the vertical movement. Let me write that down right now. Okay, so the A and the B are what we call the components of the vector. So from an initial point, A tells you how far left and right we had to move, which in our case was 4 units. And B tells us how far up or down. If A is negative, it means we moved left. If B is negative, it means we moved down. If they're both positive, it means we moved right and up. Just trying to see if I can make it a little bit bigger, but I can't. And keep it on the screen. So any questions on what those two numbers mean, the A and the B? So I gave you guys an example of the vector 4, 1. This is also the vector 4, 1. This is also the vector 4, 1. So what does this notation not really tell you? I mean, it tells you something, but it doesn't tell you something else, yeah?
What quadrant?
Yeah, it doesn't tell you where to put it. All it tells you is start somewhere, anywhere, and go 4 units right, 1 unit up. But it doesn't tell you where to start. Now, there is a common place that we usually start from. Anybody have a guess where the most common place would be to start from? Yep.
0, 0.
Yep, usually starting from the origin is the best way to do it. And if you have a vector that does start at the origin, that is called a position vector. So a vector that starts at the origin is called a position vector. Now, let's look at this one up here. The coordinates of that are 2, and what is it? 1, 2, 3, 4, 5, 6, 7. 2, 7. And the coordinates of this are, let's see, 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6, 7, 8. 6, 8. Let me erase these other ones. Now, if you look at these 2 coordinates, and let's say that that's all the information I gave you, and I wanted you to turn that into a vector. We already know what the answer should be. It's the vector 4, 1. But does anybody see what you could do with those 2 coordinates, and it would give you the vector 4, 1? Yep, Angelina?
Subtract from 1 to 1 from 1.
Yeah, subtract them, specifically the terminal minus the initial. If you take the terminal coordinate and you minus the initial coordinate, 6 minus 2 gives me the 4. 8 minus the 7 gives me the 1. So if you have a vector that's in a different quadrant and it doesn't start at the origin, that's fine. We can still figure out what it should be by doing this. So to find a position vector, if the initial point isn't at the origin, we're going to do what we just said. Here's your initial point. Here's your terminal point. In our case, for the x1, the y1, and the x2 and the y2, we had the numbers 2, 7, 6, 8. That was our initial point and terminal point. And we subtracted. It's important that you subtract them as terminal minus initial. If you do it the wrong way, what's going to happen is you're going to get a vector that points the wrong way. So you have to do terminal minus initial. And the problem should always make it clear what the terminal one is and what the initial one is, but if it doesn't, always assume that the 1 represents a start and the 2 is the second one. That represents the stop. We'll finish up with an example where I just give you 2 coordinates, just like the 2 we had right here. And we're going to turn those into a position vector. Everybody have the formula. All right. So find the position vector. Again, it doesn't really tell you which one is which, but I told you what to always go with. If you see the 1s, those are your initial. The 2s are the terminals. What are going to be the two numbers that I subtract to get my horizontal component of my vector? Yes?
4 minus negative 1.
4 minus negative 1. Yep. And what about to get the vertical component? How?
6 minus 2.
6 minus 2. All right. And how about Lacey, 4 minus negative 1? What does that give me?
3.
That would be 4 minus 1.
Oh, 5.
5. So we get 5. 6 minus 2 is 4. And there's your answer. Okay, so just starting to kind of get into vectors a little bit towards the end here without drawing them. And we're going to get into more of that tomorrow. The only time we're going to do any sketching tomorrow is if it's a word problem. Alright, so that is the homework for tonight. It's all evens except for number 1. I think that's a vocabulary question. So 8 to 22 even, 26 to 32. And ignore the questions, or ignore the directions in the book for 26 to 32. The book asks you to do something I haven't taught you yet. So all I want you to do in 26 to 32 is what we just did in the last problem. Find the position vector.